Well, thank you very much to the organisers for the invitation to come and speak today. To my great shame, this is the very first time I've been to Finland, so it's an absolute pleasure to be here. I should have visited long ago, but haven't. So I'm enjoying it very much. I enjoyed walking around the town yesterday evening. Very nice. This actually shows where I come from. We all know where Helsinki is. Probably you don't know where St Andrews is. All right? It's a very, very small town. Only 20,000 people, including all the students in the university, on the east coast of Scotland. All right? It's an old university founded in 1413, so it's quite an old place. It's one of the oldest 20 universities in the world. But it's actually, St Andrews is famous for one thing, really, and that is because that's where golf was invented, or that's where the very first golf course was, at least. I'm a chemist, right? I work in the chemistry department. So, and as chemists, we like to do three real things. We like to make things, we like to work out what we've made, and then hopefully, a lot of us like to apply things. Today, I'm going to talk really essentially about applications, right? But we do lots of synthesis of all sorts of different materials. We use lots of different characterization techniques. All goes without saying. But today I'm going to talk primarily about application, right? And really the application is of materials, in my case porous materials, mostly in medicine. Although we do a lot of work of applications of porous materials in energy and chemicals things as part of a close collaboration we have with Sasol, which is the South African South African chemicals fuel company, the state fuel company. But we've also got good collaborations with various different things and a couple of spin-out companies working in medicine. So let's talk about porous materials first of all, and zeolites are perhaps the most famous and most mature in terms of applications. There are lots and lots of possibilities of, in the olden days they were used as pigments to break colours, like the nice blue in paintings, but also they're all over the place for ion exchanges, for washing powders, in oil refineries, adsorption technologies, medical devices, catalysts for automobiles. My shoes have zeolites in because they're antimicrobial agents when they're delivering silver. So these zeolites, these porous silicates, are extremely well developed and extremely well used in industry. The reason they're well used is primarily because of their porous nature. So they've got really small pores in there, inorganic solids with pores that are about the same size as small molecules, up to sort of 2 nanometers across the pores. There's a different type of porous material called a metal organic framework, a MOF, which have sort of similar porous properties, completely different chemistry, but similar porous properties. They're metals in the corners here, linked by organic groups in such a usually fairly inflexible organic groups to leave lots of space, which in the best situation you can remove the stuff from inside there and leave highly porous materials in there. And they make particularly good gas tanks. Right? And an interesting thing is if you take a gas tank and put gas in it at a certain pressure, you can get a certain amount in. If you fill that gas tank with a porous solid like this and put the same pressure, you actually get more gas in. Simply because gases love surfaces, loves to stick to surfaces, and the immense surface area you can get, internal surface area you can get on these small pore materials makes them particularly useful. So, for example, a gram of a material like this that sits in the palm of your hand can have the same surface area as a football field, sort of, twice the size of this room. Makes a lot of surface area, which makes them particularly good for storing gases. So that begs the question, well, why should we store gases? Which gases should we store, and why? Well, of course, there's hydrogen, methane for energy. Hydrocarbon storage is very big these days. Hydrogen for clean energy. You can have environmental carbon capture. You might want to capture carbon dioxide and store that. You might want to deliver an agricultural gas like ethylene for ripening of fruits and vegetables. Most of the research pounds, the research euros that get spent these days is in the area of preventing climate change, right? Storing hydrogen for clean fuels, carbon capture gets a lot of money spent on. I don't know if you've ever been to Scotland, where I come from, but our climate is terrible. It could do with some change. So we don't do any of that. What we do is look at biological gases. They're very, very good. Things like nitric oxide, hydrogen sulfide, and carbon monoxide are potentially extremely useful in biology. Now, you'll notice that they're also extremely toxic in large amounts. So controlling how you store and deliver these things and making them useful is actually one of the things we're looking to do. So let's take nitric oxide as an example. It's a toxic gas. It's the gas that sort of car companies try to get rid of in their catalysts, out of exhaust, because nitric oxide gets oxidized to nitrogen dioxide, which is the brown pollutant gas you see all over. But it's also really important. It's in all your bodies right now, doing lots of different jobs. It's in the cardiovascular system, it's in the central nervous system. It's really important in skin repair, wound healing. Right? It's a very, very important signaling molecule that the body naturally produces and uses. And in fact, the Nobel Prize for Medicine in 1998 was given to these three guys for their discovery of the role of nitric oxide in the cardiovascular system. We know quite a lot about how nitric oxides interacts with porous materials because there are thousands and thousands of papers on the biology of nitric oxide. There are also thousands and thousands of papers on destroying nitric oxide in car catalysts. Right? So a simple car catalyst takes some bad gases, carbon monoxide, unburnt petrol, hydrocarbons, and NOx, nitrogen oxides, and turns them into much better gases. Right? That's what a car catalyst does. So we know how nitrogen-oxygen interacts with some of the porous materials because some of the commercial car catalysts use zeolites. So what about nitric oxide in the body? What does it do? Well, it does lots of different things, actually. It's one of the body's first lines of defense against infection. So it's a very powerful antimicrobial agent. But it's part of it being toxic, right? It also is one of the signaling agents to produce new blood vessels, angiogenesis. Right? It's one of the molecules body uses to kick off that process. So, of course, it's really important in wound healing then. It's also really important for opening and closing blood vessels. It's the signaling molecule for opening blood vessels, controlling blood pressure, vasodilatation, however you talk. It's also one of the mechanisms by which the body prevents platelets sticking together on the inside of your blood vessels, clotting, thrombosis. You can imagine that if you started to clot on the inside of your veins, your vessels, your arteries, that would be a bad thing. And nitric oxide is one of the mechanisms by which the body stops that. Little puffs of, not puffs, not a gas, it's in solution at the small levels, but little small amounts of nitric oxide switch off the platelets. It's also really important in the brain, but we won't go into that because it's difficult. Why do we need nitric oxide delivery materials? Well, there are lots and lots of possibilities for nitric oxide in therapy, but there's a problem. And one of those problems is it does too much. That slide shows that all over the body, nitric oxide has the potential to do something, which means that if you deliver something as a drug, there are the chances of systemic effects or side effects. So what we wanted to do was produce materials which deliver nitric oxide in a particular place at a particular time at the right dose. So that's the basic idea behind this, to reduce any problems. There are drugs out there that do deliver nitric oxide, like glycerol trinitrate for your heart is good. So We know that nitric oxide interacts with these porous materials I'm going to talk about, zeolites and metal organic frameworks. So can we use those to store and deliver nitric oxide in the right amounts that we can use in medicine? Right? So what are the issues you've got to start thinking? Well, of course, there's if you're wanting to use something in medicine, you've got to think about its toxicology, right? You've got to think about the stability, the biocompatibility, if you like. But you've also got some good opportunities here, because we do have very, very good storage capacity for gases inside these porous materials. And having a good storage capacity actually means good control in the end, as we go to it. And maybe the fact that we've got lots of different chemistries involved in these materials, as I'll show you, means that we could have biocompatibility, whatever that means. Means different things to different people, but you know. So let's have a look. This is work, a picture taken from lots of work done in the car catalyst sort of area. You know, there's lots of work done in the 70s on how nitric oxides interacts with zeolite. So this is a zeolite structure, basically, the pores in the middle, and nitric oxide tends to attach itself pretty strongly to metals, to the metals in these materials. So a zeolite is an aluminosilicate, right? And here we've got aluminium or silicon in blue, and then oxygen's shown just at the corner of these things. And then other metals are around. This one's a cobalt, structure of a cobalt, which we don't use in the medical applications because cobalt's not very nice, but we use other things like zinc in those. So we know, and we can know that actually if we put nitric oxide into these materials, they attach to the metals. They attach really quite well. Nitric oxide, for the chemists amongst you, are really quite good, not bad ligands, right? So they do interact quite well. So the actual key to the process is we know if we put nitric oxide onto that cobalt site, onto that metal site that are in these zeolites, what we need to be able to do is to ensure that when we need it back again to do its job, we can get it back. And in fact, there's a very simple mechanism. Nitric oxide is quite a sticky molecule, but water's even stickier. So if you just expose it to water, you can actually just gently release the nitric oxide in a straightforward substitution reaction. So very easy. And that's what we want to keep. We want to keep in mind doing things in a very simple fashion, so that's very good. That's zeolites, so they have the possibilities. What about metal organic frameworks? Well, they are even better at storing and delivering gases like nitric oxide because they've got much more surface area, and they also have metals. Right? This is a particular type of metal organic framework, which I'll call CpO27. It's got a very, very high porosity, and it also has metals at the corners. So this site here, 6 of them around this hexagon, is a metal site that's actually, when you make it, it just has water attached to it. And you can heat that up, get rid of the water, and leave a metal site there that's perfectly arranged to then bind something like nitric oxide. So we activate it, we dehydrate the material, then we load nitric oxide on. The nitric oxide sticks to that metal in the corner, and we can do the crystal structures and do all those sort of things, find out what it looks like. And then we can expose it back to water, and it delivers it. And the great thing about these materials is they deliver all of it. Right? So it's a perfectly good relaxation, and in very, very, very large amounts. So if you'd excuse them, there's a slight mistake here in that I chose 2 different scales. One's in moles per gram, one's in millimoles per gram for these 2 things. This is an adsorption experiment where it shows that it adsorbs between 6 and 7 millimoles per gram. And then it also, this is the delivery when we expose to water, and that delivers about between 6 and 7 millimoles per gram. So it's very good at taking in lots, and that is a huge amount of gas for these materials. So it takes it all in, and we can deliver it all, which gives us good control. So we've got the possibility, in the lab at least, of delivering the gas. Can we deliver it in the right amount for biological application. So let's pick a potential application. This is antithrombosis. As I said earlier, the inside of the blood vessels, the body's producing, the endothelial cells are producing little bits of nitric oxide all the time because it's the mechanism by which platelets are switched off to stop them interacting with each other and causing a clot. So we've got our biological model, who's a postdoc. Right? What we do with him is we strap him down and we take his blood. Right? Then what we do is we spin out the red blood cells, so his actual blood looks like this on this side. It's a cloudy liquid, platelet-rich plasma. So it's the plasma, the liquid, with the very small cells still in there. And you can't see through it because these cells are all in suspension. As you get clotting, the cells start to stick together, become heavier, and sink out of the suspension. So you can actually measure clotting, the extent of clotting, or platelet aggregation, really, by passing light through, which is this experiment at the top here. And these are experiments where we take either a zeolite, this one, or a metal organic framework. It doesn't really matter what they are. And then what normally happens, if you set off clotting, you get a response from the aggregometer. You can pass some light through. Okay? And with that, you can see that the zeolite doesn't do anything. But when it's producing nitric oxide, when it's storing and delivering nitric oxide, it completely switches off the platelets. 100% effective. The metal organic frameworks are just as good too. And the actual pictures are even better, I think, because they show that if there's no nitric oxide being produced and you put it in contact with Paul's blood, with Paul's platelet-rich plasma, you can see that there are sort of angry little clumps of platelets that have stuck to the surface. That's what happens when you put a medical device in, often, into the blood. You switch on the platelets, the foreign surface switches on the platelets, you can get thrombosis. Microthrombosis in this case. If there's nitric oxide there, it completely stops that aggregation process, and you can only see just single platelets sticking to the surface. So that's really good. And that's our sort of major, or one of the major targets in the commercialization I'll talk about as we go through, is anti-thrombosis coatings for medical devices. Things you put into the blood vessels to prevent thrombosis, prevent thrombus formation. And that's good because there's a lot of evidence now that if you start to get clotting, that's where you can get infections because it provides a home for bacteria and all sorts of things. So if you can prevent that clotting in the natural way, maybe we've got a good way of doing it. We can also take it further and start to look at actual interaction with these materials on the skin, on human skin. So this is actually quite difficult to see. It's not a very easy slide to see, but what nitric oxide does, one of the other things it does, it switches off platelets, but it also opens up blood vessels. So if you have a contracted blood vessel, you give it nitric oxide, it will open up. The smooth muscle surrounding the blood vessel will expand. And it's the way the body controls blood pressure. So, and you can see that on the skin, in this case, if we just take a zeolite and put it on the skin, or a metal organic framework, we've done both. You put it on the skin, nothing happens really. One of the delights of zeolites in particular is because they're in washing powder, they're all over your skin now, probably. Right? Unless you use liquid powders to wash your clothes. Right? If you use powders, they're all over the skin now. And 99.99% of people have no reaction to zeolites. If you do have a reaction, it's usually to the perfume, to the soap. If we then have a material which delivers nitric oxide, I don't know if you can see at the back, there's a little square of red there. That's simply the nitric oxide going through the skin and opening up the blood vessels, so you get a little bit more blood flow. It's called erythema, where you increase the blood flow and you get a bit of redness, right? Just because there's more blood flowing through the skin. And you can measure that using laser Doppler techniques, and you can measure exactly how fast and how it happens. And we can sort of see that there is no adverse reaction, no inflammation caused by if we get there. I've completely scooted over the fact that we have to control how much nitric oxide is delivered to get the dose right, but we can get the dose right to show that there's no inflammation or very little inflammation, which is unlike a sort of uncontrolled chemical way of producing nitric oxide, which is shown next to it, which which produces all sorts of ulcerated skin and inflammatory response, which is not very good. Actually painful. So we can do that, we can control the amount going, and just increase the blood flow. Now that's really good for wound healing, because one of the problems with people, normal wounds heal quite well, but wounds from diabetic people, things like that, on the extremities, one of the reasons they don't heal very well for those is poor blood flow, getting poor nutrient flow to the blood, to the thing. So having a system where we can apply some of the gas, which opens up the blood vessels, actually improves wound healing, which I'll show you a little bit later on. The other thing that's important in wound healing is preventing infection. And so antibacterial nitric oxide delivery also works really well. It's quite a powerful antibacterial agent. As soon as you cut yourself, the very first thing the body does is clot the wound to make sure it does. Once that's done, the next thing that happens is it produces lots of nitric oxide to kill any bacteria, or as the first stage of protection against pathogens. So and these materials are really quite good. We can kill bacteria really quite well, different types of bacteria, and the log reduction, for those of you interested in bacterial reduction, is up to 8, which is very good, which leads us to the possibility of doing some wound healing studies. And another potential. This next slide has some pictures of wounds on, so if you don't like that, right, look away now, right? And these are wounds on healthy animals, okay? So these are wounds that actually heal pretty well anyway, right? What we do is we don't do it actually, we're chemists, we don't touch animals, but our collaborators do, is they take animals and they little punch holes in the skin and then measure how fast they heal. So by delivering a little bit of nitric oxide, we can actually even improve the wound healing a little bit, even over healthy wounds. So the initial rate of wound closure is about 30% faster when we're delivering the nitric oxide. And this is part of one of our spin-out companies. We've got a sort of joint development spin-out company with a global, which is actually based in Pennsylvania, funnily enough, right? So they do all this work, and even in healthy wounds or healthy animals, wound healing can be improved by this. And what they're doing now is looking at then what happens when you've got infected wounds and various different things. See how fast we can improve that. The great thing about metal organic frameworks, certainly in an academic point of view, is that we have the possibility to do more than one thing. There's enough space in these materials to do different things. So one of the problems, of course, you'll see around the world, you'll hear on the news quite a lot, this idea of bacterial resistance. One way around resistance in bacteria is to have different mechanisms of killing, because it's unusual for bacteria to be resistant to everything, right? So they're usually resistant to the antibiotics because they've been overexposed to the antibiotics. So there's a possibility in our case here of delivering materials which kill bacteria in different ways. Metal organic frameworks in particular are made of metals, part of them, and metals can be antibacterial. Silver is the one you see in pharmacies a lot these days. Silver is a very common antibacterial. These are the ones in my shoes, the silver zeolites, to stop the bacteria colonizing my feet. Right? So silver, but other metals are also pretty good. Then we can do things like antibacterial gases like nitric oxide, but we could also do organic molecules, antibiotics. Maybe slowly deliver those. And what's great about the metal organic frameworks is we can fit all 3 different types of antibacterial agent into the same structure. So we can absorb antibacterial molecules, organic molecules. This is actually metronidazole, which is an antibiotic which is good for C. difficile, Clostridium difficile bacteria. But we can also store nitric oxide at the same time because they actually take up different space in the pores. the nitric oxide sticks to the walls really, really closely, whereas the antibiotic, the organic molecule, sits in the middle of the pores a bit better. And then we've also got the metals. And metal organic frameworks are held together by metal carboxylate bonds, which are not that strong, really. So actually they are quite dissolvable, soluble, right? Slowly, but the metals do come out, they do leach out a little bit. So we can make use of that fact, that instability. It's one of the reasons metal organic frameworks are often said will never be any use, because they're a little bit unstable. We're trying to make use of that application. And we can do that, and of course they come out at different rates. The gas comes out much more quickly, nitric oxide comes out much more quickly than the antibiotic, which then comes out much more quickly than the metal. So we get a multi-rate delivery of these, which is really important for one of our potential applications, which is long-term prevention of infections in urinary catheters, where these days they work for 3 or 4 days, where the real target is a month, right? 30 days. If we can sort of produce something that delivers at different rates, that perhaps we can elongate the effective killing. And how good are they? Well, these slides are quite complicated, but essentially what they show is metabolic growth of MRSA in this case, right, which is obviously a well-known resistant material. And we could show that the actual metal organic framework itself is as good as the antibiotic. Right. Measuring the different doses is a little bit tricky, because we've got a solid which we're coating on a surface versus a soluble antibiotic. So getting the measurement to be exactly the same is actually quite tricky. But you can notice that MRSA is actually resistant to penicillin type. Oxacillin is one penicillin type antibiotic, so it's resistant to that. That doesn't do anything. It doesn't really kill the bacteria at all. But we're as good as the thing. We also kill fungus, which is actually quite tricky, using these ways. And if we start to combine materials, take a MOF and the nitric oxide, just focus on vancomycin, which is here, that's the antibiotic of choice for MRSA. If we take the right metal organic framework with some nitric oxide, we're all the way down here. So we're beating the antibiotic of choice for these types of materials. And much more interestingly is when we start to expose these things to biofilms. Biofilms are when the bacteria, and they cause a lot of trouble, is when they start to form like a polymer, which the bacteria start to live in. And they can cause real serious problems, because then they start to get really difficult to kill, to disrupt. Okay? Whereas nitric oxide, probably actually because it's actually really small and gets in these places really quite well, right, is really, really good at killing lots of different types of biofilms when in situations where the antibiotic of choice doesn't do anything. So it's a real serious issue. So we're looking at designing these materials to do multiple jobs for multiple situations where we can get to these things. So that the idea is that then we get these sort of multi-rate deliveries. We have to be very careful in the loading these materials. You know, you start with the wet material, you activate it to dehydrate it, then you load the drug in, then you have to sort of reactivate it to make sure any solvent molecules come out. You've got to be really careful in that, and then expose it to the gas. But it does work, and you do get this multi-rate effect. So we get fast sterilization of the media, if you like, things like really powerful nitric oxide antibacterial agents, and then slower delivery over the other agents to make sure that the bacterial load on the surface of our material stays low. Toxicity, of course, is an important thing, and we spend a lot of time measuring toxicity, and I've only got one slide, which doesn't tell anywhere near the whole story. And if anybody's interested in sort of toxicology of these things, we could spend all day talking about it and longer. But basically, we're looking, even with materials like fairly toxic metals like nickel we get a minimum amount of MOF required to kill bacteria, and then we also get an amount of MOF which is toxic to, say, skin cells, right? It's only one type of cell, which is dermal fibroblasts. But we have a gap in between, which is the window of application. It shows that we can kill bacteria without harming the cells, which is a good thing, even with what essentially looks like pretty nasty metals. When we put nitric oxide in, actually that nitric oxide is quite a toxic gas if we have too much given there, and that reduces the therapeutic window by quite a lot. So that's a thing. So things we've got to be careful of. Now, when we take these materials and we try and take them outside the lab, right? Because that's what we're doing. We're really interested then in taking these materials. They've got potential. In vitro, they work really well for things like antithrombosis and antibacterial solids. So they work well in the lab. How do we take them up? Well, the first thing we've got to do is try and make sure we can scale up these materials, and that's actually quite a serious project in itself. How to take materials from the lab scale up to pilot scale in our and 100-litre systems of manufacture. That's loads for our very thin. We put very nice thin coatings onto medical devices, so that's plenty to last us for quite a long time. So we can do that. And then, of course, we make these metal organic frameworks as powders, and powders are particularly useless for any sort of application. So we have to think about how actually we're going to use these materials. So we have to formulate products out of them. And we can do various different things. We can make fabrics coated with these metal organic frameworks. There's a polyester, which we can take off a roll. We can do rolls and rolls and rolls of that. We can do extrusion of polymers which have these metal organic frameworks in. We can cast films. And once we've done all those sort of things, we can then start to look at how we can really start to coat real medical devices. So here's a catheter, right? It's actually a commercially available catheter produced by one of our partner companies, and you can see we've chosen a nice yellow metal organic framework here, so we've coated the material onto the top. It's actually in as a sort of with a polymer binder, just to coat the top. And we see the idea that we can coat these materials, then we can load them with gas. We then store them in foil packages, the gas-tight packages. You open the package, apply the metal, apply it, and it sort of works fine. And one of the things I'm very proud of, we've got a spin-out company, and they went away and won a nice prize, a UK prize, the Royal Society of Chemistry, Emerging Technologies. If anybody's, he's a famous comedian in the UK, probably nobody else knows, only Stuart will know, you know who he is, right? Nobody else knows who he is, so that's fine. But these two guys, Morven and Stuart, are the two technical people working in our spin-out to develop the material. And the spin-out company that won that prize is called MOFGen. And what they've done is actually identified a need, a couple of different needs, as an antibacterial one and an antithrombosis need. They've come up with a solution. They've shown that their solution works. They've got good performance. They've then worked out how they'd be able to apply it with a partner. Right? So they've worked out the formulation, the scale-up, and then got the partners interested. And then on the back of that, spun out a company, got venture capital funding, and got industrial funding and prize funding too to take it on. So that's what MOFGen does. Now, so we've got these ideas where we take these porous materials and use them as multifunctional gas delivery agents that we can then apply in medicine. We work really hard at getting the dosage right, fantastically hard at getting the dosage right, and that's something that's really important. But there's a couple of questions. One of my jobs in the last 5 minutes here was to talk, one of the things I was told to do was to talk a little bit about open science. Right? Now, I'm an associate editor for a journal called Dalton Transactions. It's whatever you might hear this afternoon, this is the best chemistry journal in the whole world. Right? Never mind Nature Chemistry and all those other things. Oh, something's going on here, it's going forward. Right? But so open access for academics is something I think that is almost a won battle. Even Nature has an open access journal now, and while it's going to take open access publication, while it takes a change in the business model for lots of journals, you can see signs that that's going to happen over time, and open access becoming much more popular these days. Lots of funding agencies say you have to have open access. Horizon 2020 in the EU, right? The ERC grants and things all mandate open access things, so that's good. But there's also something different about particularly work that's designed for medical applications, and that is who owns the data. Right? That's not the same thing as open access. Open data is not the same thing, because we've got different funders. Different people have funded our things. Some of them are charities. The British Heart Foundation funded some of our work coating catheters. Their view is that all the data behind any work that we've done should be open, because they say that it's the human race's data, and their goal is to see it used, and they don't care who uses it as long as it is used. Right? So they want all the data open. Some of their work is funded by industrial people. They want none of it to be open data, right? Because they have to talk to investors or shareholders or whatever it is, and they want to make money out of the data. So they don't want anybody else to be able to use it at all. So there's an interesting thing here. Some governmental things, we get lots of funding from EPSRC, which is the UK Research Council, and things like Scottish Enterprise, and they don't know what they want. Right? Sometimes they want it to be open data, but then they also want you to go away and spin out companies so that the UK government, UK PLC, the public limited company of the corporation of the country, makes money. Right? And to do that, often to attract investment, you've got to be able to shut everybody else out of your data. So, what do we do as scientists? Right? Do we go down the view that, especially in medical applications, it's quite a bit further forward than in materials type applications, but it's coming to us too, right? Should it be open for everyone? Should open data be there? And the arguments for that are that this data belongs to the human race. It could help people, so it needs to be open. Everybody needs to be able to use it. You've also got the argument that public money funded some of it. And to do that, public money we must make data available for the common good. Another argument is that the sponsors, particularly people like the charities, the Wellcome Trust in the UK or the British Heart Foundation, I'm sure there are similar charities in Finland, right? They don't get full value unless other people, you do the data, you give the data to everybody, and then other people can go and use it. Better access to good data means better science. Better access to bad data might mean worse science, but hey, we'll assume our data is good to start with. Then there are other arguments against open data, which are privacy concerns. So that the data could be about me, is an argument against it. Now, I guess we can solve that by being a little bit clever, right? But there's also the argument that collecting that data, managing it, publishing it in a form, actually is a cost-intensive process, and that's not fair if it's just given away. The counter-argument is you've already been paid if it's public money and stuff. There's to get that in the first place. An argument that the companies use, and in fact so does the UK government in different bits, is that if everyone has access to the data, nobody might have the incentive to actually invest in processing that data so it becomes useful. And that's an interesting one, right? How much people are willing to invest when somebody else could just go and do it as well. That's a difficult one. And the other argument is that sponsors actually don't get their full value unless the data is used appropriately. And that's the idea of data being used in the wrong way, I guess, to do things. But it's an interesting argument. Who owns the data, especially when you're talking about medically related things? I'm going to stop there. Thank you very much for listening.